Welcome, everyone. Thank you for coming this morning. My name's George. I'm a principal engineer in the customer products group. So we're the group building all of our direct to consumer, so the B2C digital apps. And essentially, the main apps you'll be aware of are our main ft.com website. And also some of our mobile digital apps. So the main FT app for iOS and Android, and also the FT Edit app. Alongside that, we look after a few other customer-facing features. We have various things we contribute to the world of newsletters, etc. But so we're on the B2C side of the business. My particular area of oversight is those mobile apps. So I look after the apps team and the FT Edit team. And we're going to talk today about something, this session used to be called the 101 of software development. It's not intended to be a sort of crash course or a boot camp. You won't come out of this as software engineers. There is far too much for me to talk about in half an hour. In fact, you would need a 3-month BSc course at a university to get that kind of an introduction into all of the different things you need to know as a software engineer to start actually writing code. But there are some important concepts which we think it's really important to convey so that you can understand some of the processes and the thinking that engineers do when they are going through from that initial brief, playing around with different ideas and taking an idea through implementation and through to eventual delivery. So I hope I'll cover some things which are interesting from your point of view, and there should be something that you feel is relevant to the work that you do. And I hope you learn some of the things about the way that engineers think and why they think like that. And I'm going to leave a lot of time at the end for questions. So we'll just have a free-form questions or things you've always wondered about software development and how it works. So in yesterday's sessions, you've seen some of the processes that we go through to decide what to build. So you've been learning about research, product design, prototyping, experimentation, and our decision-making process. And today we're going to hear about what happens when we build our website and our features and our apps, and what happens after we build them. And I really want to impress on you that the process of getting something into production and live in front of customers is only the beginning of the journey as a software engineer. So today you're going to be hearing about how we write code, how we test our code, how we get that code out to a place where our customers can actually use it and interact with it. The various ways in which code can break and what happens when it does, the things we need to do to make our systems safe and secure, and generally how we keep things running. Along the way, you'll hear at various times references to what it costs to keep software running. So we're talking about big things like the ft.com website and smaller things like a particular feature. What does the actual feature cost us in terms of the people power or the services that we need to pay for in order to make that feature work, or the cost of maintaining an underlying piece of technology that we rely on. And you'll hear later on about the work we do to protect ourselves and our customers from the people who deliberately want to break things. So we thought about the whole picture of what it means to do software development at the FT and which aspects in particular might be of interest to you. One thing we thought was really important and interesting is that the way people work within software development is quite different to how you might go about your jobs. So we wanted to highlight a couple of these characteristics. The first point we want to make is that the idea that software developers do their thinking while they're making. And the second point that we'll talk about is the idea that software development is often referred to as building things, but actually we like to think of it more as something more like gardening rather than building a house. As I said, after that, we'll come back to hear your questions. And I would encourage you to think broad and deep. It could be something you've picked up in your sessions yesterday, or a question that's always nagged you about software engineering, or a particular experience you've had when you've been involved in a piece of software getting out in front of customers. So let's dive in. The first thing we're going to talk about is this idea of thinking through making. So this is a characteristic of many jobs, of course, in the creative industries especially. So designers, writers, artists all work like this. But it's not necessarily something we associate with engineering. Engineering, at first glance, feels like a sort of mathematical concern, the idea that there are lots of wrong answers. But if you think hard enough and you use the right techniques and you work through to that logical conclusion, there is one final correct answer. But that's not how we think of software engineering. In fact, we actually encourage people not to try and find the only one correct answer. There are many different ways to solve problems. And so writing code is a creative process. And that means that engineers very often don't know exactly how they're going to do something until they try it. So we follow that typical creative process that you might know already from other aspects of your life. You start with something small. You start with an idea. You just start writing, right? You get over that writer's block and you start writing down, jotting some thoughts or making a sketch or a plan. And then as an engineer, you test it to see whether you're along the right lines. And if it doesn't work at all, you can just stop, chuck it in the bin and try a different approach. But as soon as you start to see something that is working, starting to see that something might have potential, you can adapt it and you can try again and you can iterate and you come back and you go round and round. And at all times, you're thinking critically about the approach you've taken and what the pros and the cons might be, what direction it's leading you in. Because of the complexity of the systems that we work with, the number of underlying systems that power FT.com or our mobile apps is enormous. It's not possible to hold all of the different eventualities for what might happen to a particular feature or a particular bit of code in your head at once. So there's lots of trying things involved in making software. You do a lot of having a go, seeing if it works, seeing if there's a surprise that's come up, evaluating, trying a different tack, or taking it in a different direction. So over the course of working on a feature, you'll often start with some code that solves the problem that you're trying to solve or delivers the new experience or the new feature, but it's done in a really messy way. We do it just to get it working, just to see something up on the screen, which gives you that new button or the new form or the new article experience that you're looking for. We often sketch out with fake data, for example. We won't actually use the real article. We'll use a pretend article to play around with and just to try and get something working. Because then we can look at, okay, how did I get it working? Where have I made shortcuts? Where have I left things unpolished? Where have I left the code in a very complex way? And then you go back and you find the places where you need to refine. We use the term refactor, which is the idea of not really changing how it looks, but changing the way that the code is structured so that it's more logical and so that it's tidier and easier to understand and it's less likely to break. So you do your best to ensure that the code isn't going to break, but also that if it does break, you're making it easy to understand why. So we're separating the code that we write out into logical chunks that go together as building blocks, so that if there is a problem in the future, people can understand which one of those building blocks is to blame, and they can look into the detail of what's going wrong. So we use this word iteration a lot, the idea of gradually working your way from something that's really rough, but kind of looks approximately like it should, through to something which works and is a bit more polished, and then through to something which has really got that ready for production feel. It's efficient, it's robust, it's accessible, it's secure, and it's ready for our customers. So this approach of trying first, then iterating and refining is really common in lots of different worlds of creative work. But it's really important to understand just how much of this creativity cycle we do in software engineering as well. So almost never will you get this scenario where an engineer will sit down, maybe with a pencil, draw something out, and then just type the code from beginning to end and deliver something. That's extremely unusual. It essentially doesn't happen, and we're always going through this creative process. So this means that we genuinely spend some of our time essentially guessing what might work. The systems are often so complex and so interdependent and coupled that we need to just try things before we find out whether they're going to have potential. So we plan our work as a team, and we do what we can to take the bigger ideas that might have come out of our research sessions and our refinement and our design ideation sessions and our OKRs. We take these bigger ideas, what is it that we're trying to achieve, and we try to refine them down to a set of single small refinements. So the refinement process starts with this big idea, and at the end of it, you're hoping to have a series of iterative steps, each one of which is listing some requirements. And each one of those requirements we refer to as, well, the common terminology is a user story or a ticket. So these tickets or tasks will, when they're all delivered, deliver the whole feature, the whole change, the new experience. We often call them user stories because we try to write them from the point of view of our customer, our user, and we try to say what it is that the customer should experience at each part of the way. So if you're building, for example, a new subscription form, you might have a ticket for making the form appear on screen, and then a ticket for what happens when you submit that form and the details are sent to the server. And then you might have a ticket for what the success message should look like, and then the failure state. And all of those things will be your whole feature. But we break it down into those tasks. And those individual tickets can be picked up and worked on by an engineer, and they give them most of what they need to get started on the problem. But very often as they start working, it becomes more complicated than first thought. And so that's where we do a lot of our thinking and discussing and iterating to get these small units into a place where people can pick them up and work relatively independently. And the more senior that an engineer is, the faster on the whole that they can get to a working end result. They're faster at writing code because their creative process is quicker. So when they're unsure how to do something, they're more likely to be able to work through that iterative cycle of trying something, changing tack, seeing where things might be going down a dead end, and eventually finding something which works. So the more senior an engineer is, the more likely they are at guessing what might work up front, or predicting the problems that are going to crop up in the future with the approach that they might be taking, and coming back and fixing those. So if I write my code in this way, I might foresee that it's going to put a lot of load on our servers. So if this code goes out into production right now, I can predict that there are going to be millions of requests coming into our servers, which are going to make the servers slow down to a crawl because they can't cope with that amount of load. So because of my experience as an engineer, I can see that we need a different approach for delivering this particular feature. So I'm going to talk to my colleagues and find a way that we can ship this code without the servers coming under so much load. Because, you know, hitting our servers with millions of requests can cause them to slow down, they can struggle, and that could even cause an incident or some downtime for my system or someone else's system. So we'll go back and refine the bit of code so that it doesn't have such a negative impact on our servers. And we have fantastic engineers all across product and tech, but the more senior engineer is on the whole more likely to see from their life experiences that these things have happened to them before, and they're more likely to be able to predict or forecast these different outcomes and ensure that they don't happen at all. The junior engineer is going to need help and guidance to see the potential impact of some of the work that they do. So this is the iterative process we go through, and you get better at it and more experienced at it over time, but we all still go through that same process of trying and improving and polishing. So the other point about the nature of our work is that we don't just write software once and then publish it. So it's very compared with other creative industries like writing a book or making a film. Once it's done, it's not done. At the point that it's released and out in the wild, that's when you really need to start nurturing it. So software has to be maintained. Every single line of code, every system that we make and we put out into the live environment, the production environment in front of our customers, has to be continuously looked after until we delete it. So we like to say that software is a bit more like gardening than house building. Once you've built your house, okay, so maybe you might want to paint the walls and repair holes in the roof over the life cycle of the house, but on the whole, you can trust that it's not going to fall down. If you go out and plant a beautiful new garden from scratch, if you come back in 3 years' time, everything will be overgrown. Some of your favorite plants will have just died and withered, and they'll have been completely overcome by brambles and nettles and other things. So what we do with gardens is we continuously maintain them. We continuously go out and we give things room to breathe. We make sure that the threats that are coming in from next door's garden are kept at bay. And there's this sort of metaphor for continuous maintenance and monitoring is very applicable to software engineering. So where have I got to? Yeah, so let's take a really simple example. So for much of our work in our customer-facing products, such as FT.com, we use a coding language called JavaScript. You may have heard of JavaScript. You may have heard reference to it in some of the features that you've been involved in. We write JavaScript and we put that code onto servers which run in a data center. Much of our code that powers FT.com is running in a data center based in Dublin. These servers don't just run our code. They also run various different bits of open source code that we use under license. So for example, our JavaScript will be running on a machine which is also running an operating system. So you might have heard of Linux, which is the operating system which is commonly used in data centers. And it's a low-level operating system that's very useful for software development. And the JavaScript code is also running in a sort of language or runtime known as Node.js. So we can be in this situation where we don't change a single line of our code, our JavaScript, but something changes in Linux or in Node or one of the underlying systems that we depend on, and suddenly, a year later, after deploying our code to our server, there's a new software update, or there's a new security vulnerability which has come into the Linux operating system, or there's an update that we need to apply to fix a really serious bug in one of the servers. So because these systems that we're running are complex and rely on lots of different underlying technologies, and those are being controlled not just by us but by other open source providers, we're constantly having to look after and maintain our code even though we haven't changed a line of it. So if a vulnerability is discovered in the Linux operating system, the authors of Linux will publish a patch, and they will actually say, we recommend that you upgrade. And Amazon, who run our data center in Dublin, will advise us that we need to upgrade our underlying servers which are running our code. And we need to do that quickly, because as soon as that patch is, or that vulnerability is known to the wider world, bad actors can exploit them. So they can, and they do, take advantage of these bugs. And these have, a variety of different potentials, but sometimes these things can be serious. So we have to be very aware of the vulnerabilities which have been discovered and uncovered. And one of our most important tasks as engineers is to be proactive in terms of periodically upgrading all of our underlying dependencies, so Linux and Node.js and the other libraries and systems that we depend on, so that we're up to date with bug fixes and security patches. So we say that every system must be maintained until we delete it. And it's no coincidence that John Kundert repeats this mantra in pretty much everything he says in our all hand meetings and whenever he communicates to the whole of product and tech. So he very often references this sort of mantra of keep the FT secure, keep the FT running. And then as a third item on the list, let's create some value and growth. In order to create that value and growth, we must also be doing the security and the maintenance work at the right pace. So like a garden, you have to maintain your code and your systems and your services. And there is an absolute minimum level of maintenance which you simply must do. If you're running software updates, you have to make sure all of your systems are patched and that you're not vulnerable to cybersecurity attacks. In the world of cybersecurity, there's a constant battle between people who are trying to protect websites and make software secure and the people who are trying to exploit them. And there are always new exploits being found. And then new patches will be released to secure against those exploits. And it's this kind of cat and mouse game that's being led and considered by our cybersecurity team. And it does have an impact on us. So we have to keep our systems patched so that we're not vulnerable. Thanks for that, Luke. Yeah. So what do we mean when we talk about attacks? So some of these malicious attacks might just be from sort of young script kiddies who are just getting into the idea of computers and seeing what they can do and what potential they have, and they're having a go at trying to hack websites to see what they can learn from it. It's a great way to find out how code works, how systems work. And it's quite a sort of cottage industry to see if you can try and break something. It's a fun hobby. What can I do to this popular website to see if I can break it? It's not hugely malicious, but it's something that can cause an impact. But sometimes, of course, it's much more serious, especially for the FT. It can be political and state actors attempting to do significant damage for great effect. So we have to keep our systems secure. We have to keep them well maintained. And they need to be secured and maintained even if we're not changing the way that the system behaves or the code that's running on it. So that's why it feels like gardening. If you do nothing to your garden, it will just get worse over time. You'll actually travel backwards in terms of quality. It will become a jungle and you won't see the fruits of your hard work when you first planted everything. It will actually become a dangerous place. And the longer you leave it, the harder it is to get back on top of that maintenance again. So bringing this back to software, within our software teams, we have this practice. Essentially, we say that if you build it, you run it. So once a team has built a feature, they are responsible for supporting it forever. So that brings the responsibility and the onus back on the team to build it in a way which doesn't require a lot of maintenance. There are some things that we will always have to do, like patching Linux and Node.js and the underlying systems. But there are things that we can do in the way that we structure and write our code, which will minimize the amount of work that we have to do, for example, to upgrade to the newest version of an underlying library. And I think the interesting thing for the audience here is the way that this looks from the outside. If you take a new team, if we spun up a new team in product and tech to work on a completely new project, they would give the impression of actually moving quite quickly. They would be delivering new features out to production in front of our customers relatively quickly compared with other teams at the FT. And that's because they are not having to maintain the other systems that they've built. All of their capacity goes towards building that beautiful new garden and planting new things. Their work is very quick and it's material. It looks great. You as a stakeholder or an observer can see it. But as things get further down the line and they ship more features to customers and they've got more systems that they're maintaining and more code to look after, they have to look after that code as well as building new things. So there's a natural slowing down at the rate of which they can deliver new work. And there's more at stake when it comes to prioritizing new work against the maintenance or security or updates for the old work that already exists out in production. So there are other ways of approaching this, and other companies do things differently. For example, there are other models where a centralized team one team in a business might look after all of the systems that the company is responsible for after they've gone live, and they are responsible for keeping things running and well maintained. The reason we do it like we do it is because we believe there's a massive efficiency. If something breaks or there's some maintenance be done, it's much more efficient to have the team who built the software do that maintenance. Otherwise, that external team has to come in, and the first thing they have to do is understand the system. They have to be able to reason about what's going to happen if they make certain changes, what the risk might be for shipping an update or an improvement for security. And the second thing is almost more important, which is that if you're a software engineer, you will from time to time accidentally ship code which has bugs. So we don't have bad software engineers here at the FT, but this still happens at all levels of experience. We make mistakes. And these engineers need a feedback loop. They need to understand that they've made those mistakes. They need to see the impact. If you're the person who's created a bug, but you're never the person whose problem it is to fix that bug, then you never see when you're making mistakes. And so we have this mantra: if you build it, you're responsible for it forever. It's a really helpful way to get that feedback loop, to get people understanding how to build better software just through building software. So this is the same approach really as the learning through doing. It's an iterative process. So we've talked about the cost of running software in terms of the people in the teams and what they're thinking about. But then, of course, we have the literal financial cost of running software. And that cost also just creeps up. Without doing anything, we can find that our costs increase. So we have contracts with countless external companies who provide us with a huge variety of services. We have resources that we pay for, like hosting and databases and tools for testing and for analytics and payments and for sending emails. And we have companies who provide human services to us, such as reporting on the security or the accessibility of our websites. And every single year, we have to renegotiate many of these contracts. So, for example, we have a company called Neo4j who provide us with database technology. And it's the database that, for example, amongst other things, holds all of the MyFT data. So this is what we use in the FT to keep track of which person is following which topics and has saved and bookmarked which articles. Last year, we were happily paying something like $8,000 a year for this service, just for the MyFT part of Neo4j. But one day, out of the blue, we got an email to say that their price was going up to $33,000. So $8,000 up to $33,000. And that's just what Neo4j had decided to charge us. So now we have a decision to make. As technical leaders, we can either move off that Neo4j contract and find an alternative, or we can stay and cope with the extra cost. How do we evaluate that? Well, our first option is the preferred one, but that one has a cost associated with it. The cost of moving off Neo4j will involve some engineers' time in doing that migration. And we have to think about where we migrate to, what the best solution is for an alternative. And we have to also take into account that even though we're moving to something which might eventually be cheaper and easier to maintain, it's going to be more expensive this year. So the in-year cost this year for Neo4j and the associated migration of it will be more than if we just paid that extra fee. But the cost for the future, because this is an investment not just for this year, but for 5 or more years in the future, it's going to pay off. The overall cost of ownership for this particular system is justified by doing this migration. And so this is something we constantly have to think about and talk about with other people, because it's not just us who are using Neo4j in customer products. The rest of the FT also has a contract with Neo4j that's running a lot of other services. And perhaps they might have a harder time migrating. So perhaps the right thing for us to do is to all stay with Neo4j anyway. So we have to talk about these things together and find common ground. The other thing we have to think about as engineering leaders is that we have a finite headcount. So we only have a certain number of engineers. We can't just pull in new people to spin up new teams to solve particular problems. So if we put engineers specifically on the task of migrating us away from Neo4j to save some money, then they're not available to do other work. And that work itself might be of a greater value than this particular migration. So in our teams and with Alice, our technical director, we're constantly running through these scenarios to try and work out what the optimal investment of time and money will be. But the main thing to impress on you is that all of these things that we build have a cost associated with them. So there's a cost in terms of the people who have to maintain. There's also a cost just in terms of the external factors. So Neo4j increasing their costs, or the Linux or Node.js upgrades that we have to do. And we do a lot of things to try and make these costs as low as possible. So one thing that we do is to standardize things. If we have proper formally agreed standards, particularly around sensitive things like cybersecurity and compliance, then that will make us work better as one unit. So we have common terminologies, common systems, common tools. We can upgrade everything all at once with the click of a button. And so we try to, across our engineering groups, we try to reach consensus on how we're going to approach a particular problem set, and where we can, we try to get to a place where we're standardized. So for example, in customer products, we write most of our code using the same set of tools. We tend to write our code in JavaScript. We tend to host it on a platform called Node.js. We tend to use a library called Express, and we run these on cloud-hosted software platform called Heroku. And because we have this standard approach to delivering our services, it means that our engineers can actually transfer their skills from one team and one bit of software into their next task. So you build it, you run it, kind of it becomes a little easier in that people can understand decisions which have been made in other teams. But of course, that obviously doesn't work forever, because people leave the company and they rotate between teams, and that's fine. So the thing that we want to avoid at all costs is the situation where only one person knows about a certain system. So we try to make the systems as similar as possible in terms of the code, so that we end up having less to worry about in terms of the costs of maintaining those systems. Because the more similar things are, the more that you can make those sweeping changes using perhaps a migration script that will work across all of our systems. And you can transfer people between teams, and the cost of onboarding and understanding a new system is significantly lower. So I hope that's been useful. We've talked about the iterative process. We've talked about the total cost of ownership, and how building software is much more about the maintenance than it is about getting the house up and running.